Hello, everyone. Welcome to our fourth MLPerf meeting. I forgot the number exactly. But anyways, today we'll be presenting page attention and soft, sorry, flash attention. Uh, okay, which group wants to go first?
The flash attention team can go first
Okay,
Yeah,
if there's no problem.
let's go.
yeah, that sounds nice.
Alrighty, give me a second. All right. Good evening, everyone. My name is Yalu, and me, along with Ru, Sharnav, and Henry at Group 2, will be presenting our findings on the paper flash attention. Now, before we dive into what flash attention is, we first need to have a little recap regarding attention. Ever since the groundbreaking paper attention is all you need, the self-attention mechanism is pivotal to all different transformer architectures. And basically, it's what enables large language models to actually produce tokens and response. Now, going back to this self-attention mechanism, we should look at the math of calculating attention scores and assigning values to them. So, given we have a key and a query matrix, the very first step is to compute an attention matrix. Now, if we have a key that is length n, and also a query that's also input len, then the attention matrix will take up a memory space n by n. So this grows exponentially with our input. That's going to take up a lot of memory space. So there is room for optimization here. If we can have it take up less memory space on our GPUs, perhaps we could have faster processing. As you could see here in these red boxes, the n by n, the quadratic expansion, is a major issue for the standard attention implementation. However, there's also another issue. So researchers have initially tried to solve this problem by first solve the problem of the long time it takes to calculate the computer attentions by trying to increase the speed of calculating each individual values within these each individual values within this box. However, those actually did not produce very noticeable gains. So, yes, they indeed had some speed effect, but it was nothing very significant. And this suggests that the problem was actually not bounded by the speed at which each individual value is calculated. Rather, it is bounded by I/O. So what is compute bound and I/O bound? Think of it this way. On the CPU, the time it takes to perform an arithmetic operation is 5 seconds. But the time it takes to display on the screen is 2 seconds. So in this scenario here, the result would not display on the screen until after the arithmetic operation is calculated. So it is bounded by the speed at which the hardware is able to calculate the result. On the other hand, suppose we have the same exact situation, but it takes 6 seconds for the result to be displayed on the screen. Thus, you see the result on the screen because it's taking 6 seconds to display any given result. So this is problem based on how long it takes to transfer data in between hardware. And this is central to the flash attention mechanism. Now, looking at the standard attention implementation, you see that first we will need to calculate the attention matrix with the query and key matrix that we obtain from memory. Then after computing the values for S, we need actually to save it back in memory because this is needed for back propagation. We need all those values. After writing it back to memory, we need to get the matrix again and perform a softmax function on this. Then we also we need to store this softmax matrix result back into memory because this is also part in the back propagation step. Finally, we load this softmax matrix alongside with the value matrix to get an output, so the attention score weighted value matrix. And we need to store that back inside the HBM, the memory. So as you can see here, we have a total of 6 load and write operations doing a single standard attention calculation. And now this takes a lot of time simply due to the hardware read and write. Okay. This illustrates the speed at which data can be transferred in between devices. You see on the CPU, it has a bandwidth of 12.8 gigabits per second. On the GPU HBM high bandwidth memory, it has a bandwidth of 1.5 terabytes per second. And on the SRAM, it has a whopping 19 terabytes per second. This suggests to us that we should try and do data transfer on the SRAM to take advantage of this very high speed. And this is what the team behind the flash attention did. So finally, going into the flash attention algorithm. This provides a very simple illustration of what makes flash attention different from standard attention. So you can see that immediately that there are much less load and write for the flash attention implementation. Essentially, the flash attention team fused all of the matrix multiplication, softmax application, and all these different steps into a very big kernel, so that instead of having different kernels to do these individual tasks, it's all fused together into one to save time. Flash attention has two. Yes, go ahead, Xian.
Oh, what do you mean by fuse them into kernel? What does that mean?
Yes. So as you can see here, there is a matrix multiplication. There is a softmax filter, and there is another matrix multiplication. And you see that in standard attention implementation, those are handled sequentially, and they are unrelated. They are independent of one another. All right. So we would then need we can view them as 3 separate entities. Whereas in the fused kernel, there's all the computations that happen together. So in this one step, we are calculating all the values that we need to for the attention scores and other things. Does that make sense?
No, it doesn't make sense. Where are the values stored when we are calculating using the fused kernel?
The values are loaded from the HBM. This is a very rough high-level demonstration of the general concept behind it. I will go into details about how you can calculate the matrices P, O, and S from the values listed here, to be specific, the L and M. Would you mind to wait a seconds
Yeah,
for my
seems like I asked the question too early.
Right. Yeah, this is just to give a very high level demonstration of why this the general idea behind flash attention. Okay. Now, flash attention uses something called tiling to split up the large matrices. So if you think about the previous the GPU high level demonstration, you know that SRAM is roughly 20 megabytes or 40 megabytes on a 100 GPU card. That is very small, so it won't be able to fit a very large softmax matrix, attention matrix. What we could do is to break that big matrix down into smaller blocks and process them accordingly. So in subsequent demonstrations, I would stand for row, J for column, KJ and BJ. This means that we are splitting the original key and value matrices vertically into different columns. Basically, we are decomposing a very big matrix down to its smaller components and trying to calculate the softmax from there. We then load the query out L and M matrices from the memory. Query I means that it is split horizontally. So these are values obtained from a previous iteration of the attention calculations. O is just the weighted attention score weighted value matrix. Now, going back to L and M, these are two variables that contain data needed to perform a softmax. And here just signifies the largest value within a single matrix. Fx and the Lx are values necessary to compute the actual to implement the softmax. Since the softmax itself is just e exponent xi over the sum of exponent xj. The reason we have mx here is to ensure numerical stability, because e to the power of x1 can get very big if as x1 increases, and this could lead to overflow problems. So that's why we have mx here to ensure numerical stability. The basic softmax function itself is defined as such. Thus, you can see that we can calculate the softmax matrix with a combination of N, L, M, and L. These are all we need to calculate the softmax. And this would, in fact, give us O, as you see here. So in each iteration, we calculate these respective values. Then we would update these values and store them back into the big memory. This is an iterative process. We continue to perform these iterations until we have gone through all blocks, all partitions of the original key, query, and the value matrices. Right. So this is how this is a mathematical proof of how we could actually decompose the big softmax matrix into smaller partitions. So as you can see here, if we were to divide a big matrix X into partitions X1 and X2, then we are still able to build a softmax matrix of X using just its components as described within here. Another idea central to flash attention is recomputation. You can see that nowhere in here are we storing the actual attention matrix, that is P and S. So we are not using up n by n space anywhere, and this reduces memory space. Let me show you a diagram of how this usually works. The orange blocks on this diagram represent the SRAM, the high-speed memory that could process has a bandwidth of 19 terabytes per second. While the green blocks here are the generic high bandwidth memory that are much slower than SRAM. You see here, we are calculating the attention values in the under the SRAM, and we are storing everything to the HBM. So there is a minimal interaction in between the slower HBM memories. In this way, we are performing the computations much faster than simply transferring values in between the high bandwidth memory. On the right is what the authors of the flash attention suggested as his kernel. You can see in the original attention standard attention calculation process, there are a lot of split up into matrix multiplication, softmax matrix multiplication, whereas in the fused attention, as shown previously in my model, every single step of the calculation is merged into one slightly bigger step. And since we are not reading and writing in between HBM, this actually takes much less time than all these steps combined together. So that is the gist of flash attention. Here is the algorithm as defined by the authors. If anyone has a question, they can ask me now. Otherwise, I'll be handing it over to Henry. Yes, Zixian.
Okay, can you go back to your previous slide? So everyone else, do you understand what this graph really mean? Because this is the core idea of flash attention. So we're looping through the K and the Q, sorry, KQV. So these big matrices are stored on the HBM because they are so large that the SRAM that only has 40 megabytes could not store all of them. So that these big matrices are stored in the HBM. And then, do you remember the I and J Yalu showed previously? We're iteratively looping through. So we first divide the KQV into different blocks so that each time we send one block to copy from HBM to SRAM, and then everything compute stays within the SRAM. So that by doing this, we can prevent heavy loading, storing and loading these big matrices again and again. By doing this, we only need to load it from SRAM one times and store it from SRAM to HBM one time. Does everyone still have any other questions? Don't be shy and just ask it if you do not understand, because I want everyone to really take out the core idea for flash attention here. Ian, I cannot hear you.
Oh,
I'm sorry.
whoops. Right, so you only have to load them once I was gonna ask what you do with the KQV matrices, but I think that's actually what we made our presentation on, so never mind.
Yeah. So the general idea is that the paper seeks to address why it's taking so long to calculate the attention matrix, and they realized that it was an IO-bound issue. It was taking too long to transfer data in between the high-bandwidth memory on the GPU. So they wanted to move it to the faster hardware within the GPU, so that the process is sped up. All right. Okay. If that's all, I shall be handing it over to Henry. Give me a second. Sorry.
Yeah, hello. I am going to introduce like how they actually perform this computation on the GPUs. So I assume you all familiar with like some basic idea of CUDA programming, like the relationship between block and threads and streaming multiprocessor. So here's the okay. So here's the basic idea. Thread is the basic compute unit on the GPU, and block is like includes some number of threads. So yeah, so and then a block has a lot of threads in it, and there's another concept called grid, which is like blocks is inside the grid. So in general, it's like grid, blocks, and threads. So and then these are the threads and blocks and grids are all executed on streaming multiprocessor. So yeah, and one block has to be assigned to one streaming multiprocessor, but like one streaming multiprocessor can have multiple blocks executed at the same time. So let's go back to our case here. Let me do annotation. So here is like the standard attention algorithm, which like one block only execute one attention head. And so they want to parallelize this. So they make here's the attention matrix. They make one worker for the forward pass, they make one worker to take care of one row in the attention matrix, and worker is basically a thread block. So there are like, in this case, there are 5 thread blocks. And for backward pass, they do it a little bit different. They do it like they divide it by columns. I will talk about it, like why they do it later. Let's go to the next slide. So here's the basic idea. Worker 1 takes the in the forward pass takes the rows when computing this, and like the worker can like take more than one rows, so it can take like 2 or 3 rows at the same time, and backward pass is like this. Wait. So here's the more specific on forward pass. They call this like slice K scheme, where they slice KV into 4 warps. One warp is basically, warp is like a part of block. It's a kind of block. One warp normally contains like 32 threads. So they divide K and V into 4 warps, and then they here is more example. So the blue, red, green, orange are 4 warps, and they perform computation to corresponding value of K, Q and K. And then after they do it, and then they will write those results back to shared memory. And then they need to do sync. Synchronization is a very important process in GPU. execution because the GPU needs to wait for the last thread to finish their job. If you don't wait for it to finish, you get some wrong value. And synchronization takes a lot of time in GPU computing. And then after that, they do softmax, and each portion times the corresponding V value, and that is the forward pass. And for the backward pass, yeah, here's the backward pass. Backward pass is like a little bit more complicated. So here I use 2 workers to I use 1 worker to take care of 2 columns, and for sorry, so the final goal we want is to compute the gradient. The gradient the delta L divided by delta Q is the gradient we want. So after we get the gradient, and then we can update our weight. So yeah, here's the left side here. Here's the chain rule we are using to get the gradient, and here's basically how we compute it using the aggregation. Like each worker takes 1 part because we have 2 workers here, so each worker take 2 columns, and yeah, and that's it for the backward pass. So now I'm going to talk about the total runtime and HBM access. So you can see here, the flash attention algorithm has like, oh, Zhixian has a question. Yeah, go
Yeah,
ahead.
my question is about the previous 2 slides where you have your drawing. Yes, this one.
Yeah, this one.
Yes. So you are saying that we divide K and V into different wraps so that we can calculate them at the same time. So on the right-hand side, the blue, red, green, and yellow all happen at the same time.
Yeah,
because they're parallel.
that's
Okay.
true.
Okay.
But they need to sync here. They need to sync after. So it takes a lot of time still.
Okay.
So this is flash attention 1. And they solve this by having flash attention 2, but we don't cover it in this presentation.
Okay, just to make sure, is the K divided into different wraps here? Are they
No, they are
the
divided.
same instance that are passed to SRAM? Because we also divide the K and V to pass through the SRAM.
No, they only have, like, for example, warp 1 only has can accessible to its own data, to its own memory. So they only copy part of K to their shared memory. So warp 1 has its own shared local memory. Sorry. And warp 2 has its own shared local memory. Sorry. And they have another thing called shared memory. So they write their local memory after computing. They write their local memory, like the result to shared memory here.
Okay, I'm a bit confused. So is the K and V here the smaller chunk of the big K and V?
This one, yeah, this is like part of K.
Okay,
It has like the value part of K. It contains part of.
Just to make sure I understand. So for initially we have big vectors, matrices for K and V. We first divide them into smaller blocks, smaller chunks to pass into SRAM. And then inside SRAM to utilize the GPU, we further break them up into even smaller chunks into wraps, and then we pass to the compute unit. Is that
No,
correct?
just split it once. Like
Oh,
split,
once.
yeah, just the whole cake, and then split into 4 warps. Yeah, and that's it.
Oh, so the big
Warp is
KV.
basically block.
So the big KV is split into four wraps.
Yes, it's like in normal cases 4. They can do like 8 or however. It depends on how you implement it.
Well, if they are, do each wrap all store in the SRAM?
They don't store like at once. They can like store the whole at once. So they just store part of the data and then they finish the computation and then like do the next.
Okay, here's the counterintuitive part that I do not understand. Previously we said that we pass to SRAM one at a time, but in here you are saying that these can be parallel. They can be computed at the same time.
No, I said like it cannot fit all, right? So it can just take part of it, part of the K and part of the. We don't need when doing here, so we just take part of K here.
Can you draw it step by step, probably?
Like for example, this warp here. How that? Because sometimes we cannot like even know the whole warp. We can probably like know the half warp, like fit the half warp, fit the memory from HBM to half the blocks and warp, and then we can do like computation on this part.
That
And
is
then
okay. At time 0, that's what you do. What about at time t+1?
then we can do the rest.
Okay. Well, what about next step?
If we can do like all parallel, like then we cannot, sorry. It's so large and we cannot load, then we have to do it one by one, do the
Okay.
warp.
Okay. So the
But
blue, red, green, and yellow happen sequentially.
normally they are parallelized because it won't be that large.
Okay.
So I think it depends on how you implement this. Yeah, I think so. Because each warp has its own local memory. So they have the ability to process its own data at the same time. So if you assign the memory very well, so you won't waste any time to do them by sequential. So if you don't want to waste your compute power, you can like do half in warp 1, half in warp 2. Yeah, go ahead, Elhan.
Yeah, so I also kind of agree with Jishan's confusion here. So I mean, if we assume that the V can be, let's just assume that your picture here, you have V and K and Q, and then I mean in your schematics, all of these matrices are divided into 4 warps. And for an hypothetical scenario, if you could run all 4 of them in parallel, then there's no point of splitting them, right? You could just basically load the whole thing.
No, because like as I mentioned above, like if we don't split them, like which is like go to that.
I know when you are doing the matrix multiplication, it is parallel, but
Mhm.
Uh-huh.
it is counterintuitive that Well, first we said that SRAM is very limited, so that we can only do this amount. For example, warp 1. But you are saying that we can do all of them together, and but it is we
But
cannot fit
I
everything.
think
in
like
SRAM.
I mean is like low part of it, not all at the same time, right?
Oh, are you saying that okay, we divide into 4 blocks, and then we for the 4 blocks, let's say we load 10% from the first block, 10% from the second block, 10%, 30, 10%, 4. And then we do these 10% at the same time. And then next step, we do another 10% across
Yeah.
the 4 blocks.
If I understand the paper correctly, yes,
Okay.
you do.
Okay, yeah, then this makes more sense.
Mm-hmm. And do they only, I haven't read these papers, do they only talk about the GPUs from NVIDIA, or is it, in general?
No, just it's all based on CUDA programming
Okay, so
from the beginning to end. It's all CUDA.
okay, yeah, because these lingos are all in CUDA. So in general, if you want to implement the
No.
matrix multiplication, regardless, you would be doing like this. You would be dividing into which are like bunch of threads, and you'll be doing like that. Okay, but I should probably look like what additional thing they're doing in the flash attention.
I think only CUDA can do this like subtle operations. Like they can like operate the exact threads on the blocks. Yeah.
Okay, just adding on to that, this is the limitation for flash attention 1, because it is highly tuned for their hardware specifically. And in their flash attention 2 paper, they address that they include a PyTorch version for flash attention, and they also implemented a Triton, the Triton kernel that can do flash attention. And then Triton kernel, and if it's implemented in PyTorch, then probably there is a ROCm version, because ROCm and PyTorch is compatible. And there's a Triton version, so Triton kernel is also supported by ROCm. And I know that flash attention 2 is supported by AMD GPUs by ROCm.
Yeah, okay, that's good.
Well, I'm not sure about flash attention 2.
Flash attention 2 is basically keep K and V into just like Q here. Keep K and V accessible by all warps and split Q instead. That's the main difference.
Okay, yeah, that's all good. Yeah, please continue. I do not have any other questions.
Yeah, okay. So here's the runtime analysis and the blobs. So the runtime is basically almost 6 times faster. And for the M here, M is here's the bound for M is D to ND. D is basically D means attention head, like the head dimension. So at M is the size of SRAM. So you have to know at least one head to the SRAM, which is the lower bound, and the upper bound is to load all the head dimension, all the heads, which is N times D to the SRAM. So M is basically for the worst case is big data N times D. And if we substitute M to here, then we can get big data N times D. So in this paper, because this is the best we can get, because we at least need to load all the heads to the SRAM at least once, because we need to compute them. So that is the best we can get. That's why the flash attention is very good. And I think, do you have any question? If no, then let's hand to Anav.
Henry, from reading the paper, I think we only load one warp at a time, not all 4 warps.
I don't know. I think I read a article. I think they mentioned, I think you can do, it depends on how you implement it.
Yeah, it depends on implementation.
Yeah. Any other
Yes
question?
or no? People who have the sparse box sparse attention.
Right. Would you be, do I have control of the slides?
Unfortunately, I don't. You are not. Your name is not in the list of options of who have slide control, so you're gonna just have to tell
No
me to
problem.
do it.
Oh,
No problem at
can
all.
you wrap up the slide because we're kind of out of time?
Yeah.
Thank you.
So, thank you, Yalu and Henry, for your introduction of the topic. I'm quickly gonna introduce everybody to a special form of flash attention called block sparse flash attention. Next, please. So as you might imagine, some of the blocks that we divide Q, K, and V matrices into using the tiling process will turn out to be full of zeros. Now, as we've been seeing throughout this discussion of the paper, while we're concerned with both computation time and memory access, reducing the number of times the algorithm actually accesses memory is the key focus of the paper. Therefore, it makes sense to simply not compute blocks which are full of zeros. Now, how does the algorithm decide which block to compute and which block to ignore? It does that through a regularization technique called dropout using a special sort of mask matrix called a sparsity mask matrix. What is a sparsity mask matrix? It's simply a matrix full of zeros and ones. Each element of the matrix corresponds to a block of Q and V. If the mask matrix contains a 0 in that index, attention score for that corresponding block is simply not calculated. But the question is, how is the mask matrix generated in the first place? How do we decide which block should be calculated and which block should be skipped? So there are essentially 2 types of mask matrices. Number 1 is predefined. Next, please. And number 2 is a dynamically generated mask matrix. Next, please. Now, how do we arrive on predefined mask matrices? Next, please. Number 1, known structural patterns. For example, in some natural language processing models, like they know that certain positions in the sequence contain more valuable and consequential information. Therefore, the mask matrix is designed in a certain way to concentrate on those indices. Next, please. Predefined rules based on specific problem domains, rules can be established to determine which blocks are more likely to be important. Next, please. Obviously, learned patterns. Patterns observed during the training of previous models or other models can be used to determine mask for upcoming models. Next, please. Other type of mask matrix, obviously dynamically generated mask matrix. So 0 blocks. So the algorithm does an early pass on the entire input, and it goes over and identifies blocks which are entirely 0. These blocks do not contribute to the attention mechanism and therefore can be skipped. Next, please. Blocks with low variance. So basically, blocks with low variance may contribute insignificantly to the final result and can be considered for skipping. Like when a block has low variance, the values are nearly the same. The redundancy means that the block carries little unique information and therefore is not very helpful, is not a very distinguishing feature between inputs. Next, please. Another technique, Ian, please go ahead.
Hi, you mentioned low variance blocks are candidates for skipping. So do they know that they're low variance blocks because there's some kind of program calculating the standard deviation of these blocks as you're iterating over them?
Yeah, exactly. So basically, standard deviation or average is how, sorry, not average. Standard deviation is basically how they determine which block has low variance and how close the values within a block are.
Right. And then since you're gonna want to know the standard deviation for like all the elements, does that contribute any considerable memory?
So not really, because the block has to be loaded into SRAM anyways, right?
Yeah.
So basically, the computation part is skipped. Actually, that's now that I think about it, it's quite a good question, because it would be wasteful to load it into SRAM.
Well, I'm just maybe
Because
I
that
don't
would
fully understand. Is the standard deviation of these elements calculated during training?
So dynamically generated, yes, dynamically generated mask matrices are not very commonly used, because as you said, they are an extra burden on IO and computation. Even if small, they are certainly an extra burden on the IO and the computation. And they're generally not used. It's not a very common practice, but yeah, I forgot what your question was.
Oh yeah, sorry. I was wondering. I'm not sure if I fully understand the low variance part. Is the low are these standard deviations calculated for positions in the input matrix during training? So during training, you input all these different sentences and whatnot, and then you calculate which elements on average have the lowest variance. Is that what happens, or is this variance coming from somewhere else?
A very, very crude way, yes. Basically, obviously, the sequences are tokenized, right? Like embedding layer converts it into numbers, correct? So they just the standard. So consider 100 by 100 matrix. Let's say we break it into chunks of 2 by 2 matrices. So the standard deviation of those 4 numbers is calculated at once to determine whether that block is significant to us or not. Then we go on to the next block, then we go on to the next block. So it's not like it's not the entire matrix for which the standard deviation has to be calculated at once.
Oh, well, right. Yeah, I guess I was referring to like they calculate a standard deviation for each element, but you're saying they like calculate for like a block of elements, a group of
For a
them?
block, yeah. So we split KQV into smaller blocks, right? So it's calculated for each block.
Got it. And this is calculated during training?
Yeah. For dynamically generated mask matrices, yes.
Yeah. All right, awesome.
Thank you, Ian, for that question. Now I'll quickly go over to the last technique, which is thresholding. Basically, thresholding is also another technique where the average of the values in the blocks are calculated. If the average is above a certain threshold, that block is considered significant, calculated. If the average falls below the threshold, basically that block is skipped. And if there are no further questions, I would hand it over to Arush to continue our presentation.
All right.
Yeah, what's your question again?
No,
I'm sorry, did someone
so
ask
yeah,
what my question was again?
I
Yes,
think
raise your
if
hand.
you do not have another question, like you
Oh,
could like lower the
yeah,
hand. Oh,
sorry.
no, that's completely fine. Thank you so much for your attention, people.
All right. Thank you, Arnav, Galu, and Henry for a great presentation so far. Now we'll go over a brief look at an evaluation and possible improvements on these models, along with real-life limitations and how those might apply back to us for our work in SCC. Oh, sorry, I think I skipped ahead one slide. Yeah. So first I want to talk about improvements real quick. And more specifically to talk about improvements, I want to give a background on sparse matrices, which are a special type of data structure most commonly used in data science or for training very large data sets where specifically what happens is, as you might notice in the matrix on the left side, there are a lot of zeros. And what's happening is now inside your memory, you've allocated space for the entire matrix, but a lot of the space is being allocated towards zeros, which aren't really going to have an impact on whatever calculation you're trying to do with the matrix. So instead, in certain cases, it's more efficient to convert this matrix into a sparse matrix, where instead of loading the matrix in traditional form, you load a row, column, and value set for every single non-zero point. This is what you can see on the right side, where obviously with zero-based indexing, you have row 0, column 2, the value 3. And let me just try to annotate. So this column 3 here comes from, as you can see over here, column number 2 in zero-based indexing, and row number 0. So we store the coordinates and we store the value. And as you can imagine, when you have a very large number of zeros, it's more efficient to use 3 data points to store one value than it is to store the entire matrix. Um, and for this specific case, which is very common, for example, if you're using one-hot encoding in some sort of data transformation that then gets used in training a machine learning model, but also for many, many other cases of like very large data sets. And here you see that now there's a special version of flash attention called block sparse flash attention that's able to make use of sparse matrices to further reduce IO complexity, building on everything that Yalu, Henry, and Arnav have talked about before. This makes it even more relevant to the real world because a lot of data science work and a lot of raw data sets often just have very large numbers of zeros that would not really make a difference. And now the next improvement that we see, let me see if I can clear this. Yeah. So the next improvement that we see comes from the research paper benchmarking training time on flash attention models on different, flash attention mechanisms on different models. And the memory efficient design allows larger context windows, but also allows very large speedups, 3 to 3.5x, depending on each model. This is a major improvement to the existing state of the art because obviously um, a 3x improvement is really massive. And at the scale of compute resources we're talking about, this is something that's, really, really hard to achieve through like conventional efficiency improvements. So additionally, by allowing larger context windows, we're able to improve the usefulness of these models after training and in inference tasks, which may be relevant to us in SCC. All right, sorry about that. Now moving on to the next slide. Yalu, I think my controls aren't working anymore. All right, thank you. So now I want to talk about the effect this algorithm has on different models. And to begin with, I would like to draw your attention to the graph here on the right side of the screen. I want to point out how the normal attention mechanism sees a 20x improvement through something called the Linformer attention, which is not what this research paper is looking at, but it was another method at the time. And then, notably, by using either flash attention or block sparse flash attention, which in this case, there's no difference, we're once again able to get a 2x speedup, leading to, in total, a 40x speedup in, a 40x reduction in memory footprint, even as sequence length increase. And what's very useful, of course, is it allows, if you're memory limited, which you almost always are, it allows you to have much, much larger sequence lengths for your training or for your inference tasks. Additionally, this means that you're also able to improve your performance in benchmarking, and any improvement in efficiency is always a win for environmental sustainability as well. And next slide, please. Now I'm going to talk about the graph on the left side, and more specifically, let me see if this works. Yeah. So more specifically, I'm going to talk about exact attention versus approximate attention. Exact attention is the traditional attention mechanism, which was explained earlier in this series of talks that we've been giving, and it's the standard attention that everyone thinks of. Now, approximate attention is a less computationally intensive algorithm that uses heuristics to approximate the attention mechanism at a significantly lower computational cost. In both cases, this can lead to runtime improvements. And in the graph over here, if we look at block sparse flash attention, it's got the shortest runtime for every sequence length every single time. And then we also see for flash attention, it keeps pace with block sparse flash attention up to approximately 256 as the sequence length. And then block sparse flash attention is more efficient, but flash attention does remain the second most efficient implementation, up to some point between 512 and 1024 as the sequence length. And then it becomes a little harder to benchmark whether it's good for you or not. But notably for us in SCC, this may be more useful to us because we may be working with smaller sequences, although we're not entirely sure yet. And now I just want to talk briefly about the limitations of this model as well. I know this was addressed in a question earlier, but the biggest limitation is that, of course, this has only been tested for CUDA as of this paper. There are 2 more flash attention papers, so this may have changed. But at the time of this paper, it was only for CUDA, so it needs to be rewritten for every GPU and for every kernel, including our own GPU and kernel that because we'll be using AMD at SCC. The second limitation is that the improvements brought about by flash attention, as the name suggests, only applies to the attention mechanism. And so, as you may remember from our talk about transformers and attention a few weeks earlier, there are other mechanisms that play a role in encoder, decoder, and transformer blocks as a whole. So these improvements do not apply to every stage of that process. And so there is more room for improvement by improving those processes instead. And lastly, as of Flash Attention 1, the testing had not been conducted in a multi-GPU setting, which is what we will be using for our own cluster. However, this may have changed in Flash Attention 2 or 3. And that's the end of my section. If anyone has any questions, please let me know. All right, well, thank you so much.
Thank you for the great presentation. a very thorough talk on flash attention. It's very good. It's great. Just a friendly reminder, next time we don't need to focus so much on the evaluation on the performance graphs. Okay.
Okay, for sure. Yeah.
Okay, I know it's a bit too late. Let's take a 5 minutes break and then we'll back with our page attention. Okay. Yeah. It's been 5 minutes. Let's wait for some others to come back. Feel free to share screen, Ian, for your presentation.
Hi guys, welcome to the presentation. Their presentation seemed like it was about reducing compute. Ours is more about reducing memory.
Oh, their paper is also reducing I/O, reducing
A lot of stuff. Sorry, I'm oversimplifying. Big grand view. Okay. Sammy, you ready to go?
Yeah, I'm ready.
All right, swag.
All right. So, hey guys, our presentation is on page attention and the LLM. It's by me, Ian, Jacob, and Flavia. Next, please. Next. Okay. KB caching. Oh, go back one. KB caching occurs during the multiple token generation step and only happens in the decoder. Next, please. Since the decoder is casual, the attention of a token only depends on its preceding tokens. Without a KB cache at each generation step, we're recalculating the same previous token attention when we actually just want to calculate the attention for the new token. Next, please. Oh, for example, without KB cache, we have to calculate the attention for the tokens artificial intelligence is before being able to calculate the attention for the token the. Next, please. Then in order to calculate the attention for the token future, we have to calculate individually the attention for the tokens the future is the once more. Next, please. Lastly, to calculate the attention for the token of, we have to calculate first for the tokens artificial intelligence is the future, and then we can calculate the attention for the token of. Do you notice how long that can take? Next, please. This is where KB cache comes into play. By caching the previous keys and values, we can focus on calculating the attention for the new token. When calculating the attention scores of the K+1 token, we do not need to recompute all of the previous keys and values, but rather take it from the cache and concate it to the current vector. This results in faster and more efficient text generation compared to not having a KB cache. Let's go through an example of this. Next, please. In the image, we have a KB cache that stores previously calculated attention data for the tokens artificial intelligence is. Next, please. When calculating the attention for the next token, we don't need to calculate the previous token's attention. Next, please. The KB cache is then updated to include the previously calculated token and proceeds to do the same thing to the current token of. One quick thing to note for the rest of our slides, we'll be replacing the numbers that you see in the KB cache with words. This will be better for understanding the rest of the presentation. Next, please. So KB cache acts as a memory bank where the model stores key and value pairs derived from the self-attention layers for previously processed tokens. By storing this information, the model can avoid redundant computations and instead retrieve keys and values of the previous tokens from the cache. Tishan, yeah?
Can we go back to previous slide? So you have been saying that it saves a lot of compute, and what does that mean? What is the saving, and what is KV cache? What is, yeah.
It saves time, just because without KV cache, we're recomputing everything over and over again. With the KV
Recomputing what
cache, we just
exactly?
have to the previous tokens.
The previous tokens in terms of what?
And I guess like if our current token is we'll be like recomputing the attention for artificial intelligence is like those tokens again. With KV cache, we kind of store, I guess, the attention of like our previous tokens and concate the attention for the current token.
That doesn't seem right.
Okay. I guess maybe you can jump in and help me out then.
Yeah, so I think by attentions, what's being discussed here is like the K and V vectors. Every time you iterate through your model, it's going to generate a new word. But in order to generate that new word, you need to do matrix multiplications that involve the KV. And so it would be a huge waste of time to take your whole sentence, plug that into the model, and compute the next word every time, because you already have the KV matrices computed the very first time you plug in your sentence. So if you just store those elsewhere, you can call them back out of memory the next time you generate a word. And that means that you only need to plug in one word each time after you plug in your initial sentence. So your initial sentence is going to have multiple words. You're going to plug that in. It's going to generate KV matrices. You're going to generate one word. And then the next time you iterate through your model, you only need to plug in that new word that's been generated, because the K and V matrices have already been computed for all the previous words. That's what's being cached, is the K and V matrices.
Not too quite. Well, yeah, but you missed the core idea. Okay, so can someone give me the annotating access? I do not have annotate access. Is it out of your control?
For the Zoom meeting?
Yeah.
Yeah, no, it's not my control.
Okay. Well, first of all, in normal attention, okay, so we are saving the compute that, well, let's say we have, can you go to the slide where we talk about the artificial intelligence?
Sorry, can you repeat? Which slide is that?
Go to previous slides. I don't know. Yes, this one. So in here, so the way so I need to correct Sammy on calculating the attention. That is not correct. We know that when we're, yeah, can you just stop sharing for a bit? Let me share. Let me go to a whiteboard. Okay, so in the previous setting, we'll have let's represent T, artificial A, intelligence I, something, right? Is, let's say we're on token is. So we know we need to pass this into through our attention head. To get our KQV. But since all our previous tokens are generated and they have been passed to head for one time, well, let's say, okay, let's do this. So we have passed in the AI is into head, and we get K, Q, and V. The query will be is. And then the next time when we're doing it, we have the AI is. And now we need to pass all of these into the head, attention head. Right? And we know that from the previous time, we have already calculated the AI through the attention head. So these values are already calculated in the previous iteration, okay? But if we want to keep generating starting from is, well, let's say future f. So when we're doing this step, we need to calculate the Q and V for the A and I. Okay, but these and is. But these four tokens, the KV has already been calculated in the previous iteration through the head. And we are fixing the model weight and our input, of course, so that these values, the K and V, can be cached so that we do not need to recompute them again. Understand? Following? Does the other group understand? Okay.
Yeah.
Okay, so with the cache, let's say we store them into our fancy HBM. Now what we can do, because in our previous iteration, we have to pass in this entire sequence into the model again for next token generation. But with the KV cache, because we have this, we have already calculated the K and V after the attention head. So these are already calculated, so we do not need to store them. So we store them into HBM. Now, if we have a new token that is generated, the artificial intelligence is the future. Let's say we have a period. Okay. Now, if with KV cache with KV, then we only need to pass one token instead of all the previous tokens and recompute going through the attention head again. Okay? So now when we pass through the head, because we have never computed the KQV through the attention head for our period, so this is completely new, and the model is the first time doing this. It will give us our query, which is our period. And then for the K, we know it will be also a vector, because assume we have the number of heads is 1, so that the shape is the model, right? But we know this is only the only attention head for the period. We need the previous informations to calculate the attention. What we do is that we go through the HBM to give it back our cache values, right? So in here we have the T, we have A, we have I, is, and then we also have another one for F, future. By doing this, we do not need to recompute all these in orange again. So that is what it means using the KV cache. We can save compute because we already computed these in the previous iteration. So now we only need to store this into HBM and we load them from HBM when we need it again. And then same for the key, because we have W, Q, and we have WV, and we have W K. And each of them are different outputs. So we also have another group of cache for values specifically. And these are also stored in the HBM. So when we need them to compute the attention, we load them again. And then we load them again together with a period. Understand? Anyone following? Okay,
Yeah.
so now with these, our complete K and V, we can compute with the query, because next token where our query is only one token, and our input is one token, so that the query will only be one token. We compute Q and K into our O. This is our attention score, and then pass through softmax, and then multiply with V, and that is our attention score. Okay. Raise your hand if you understand what KV cache is. Okay. For those who are not raising your hand, do you have any questions for me? Feel free to speak up. Unmute yourself. Okay, yeah, if not, then this is KV cache. Next time, you need to do a better explanation on the KV cache. It's the important concept. And if you want to check out more on the KV cache, I have a recording that I took last night, and it is posted in the Google Drive. Okay, yeah, sorry for interrupting. Please continue with your presentation.
No, that's all right. Yeah. If anything, it's better for everybody to understand it better.
Yeah, for next time, don't
yeah,
let me to explain it. I'm hoping you are the expert, okay?
No, yeah, but we already talked about getting feedback earlier, so yeah, it won't happen again with, cool. So if you yeah, so next, cool. So this is the KV cache memory usage. There's a equation for it. It's 2 times precision times n layers times the model times the sequence length times the batch. It's 2 from the 2 matrices from K and V. The precision is the bytes per parameter. The n layers are the layers in the model. The D models, as I mentioned, of embedding. The sequence length is the length of context and tokens, and the batch is the batch size. And I got this example from a video that explains KV cache and how big its memory can get. So they were getting it to be a total of 180 gigabytes, and it was calculated by 2 times the key and the value vectors, 2 times the bytes 2, which is the bytes per FPS 16, 48, which are the number of layers, 7,168, which is the dimension size, and 1,024 for the max sequence length, and a 120 for the batch size. And it's a cache size example for OPT30B. And the bottom right is the face I made when I saw that. 180 gigabytes. Yeah. Okay. Let's see. Oh yeah. Given the current trends, the GPU's computation speed grows faster than memory capacity, and memory will become an increasingly significant bottleneck. Next slide.
Okay, so there are like 3 types of memory waste with KV caches, but firstly, it's internal fragmentation. So because the total sequence length of a request is kind of unknown, so in order for it to play safe, the system allocates contiguous memory to fit the maximum length. But most of the time, it's just never reaches the maximum length. So over allocation of the memory happens due to this, and this is called internal fragmentation. And next. And the second memory waste type is reserved. So with KV caches, we reserve a certain chunk of the memory to run our request. But with memory being consumed gradually, so these reserved memory chunks cannot be used to process any other shorter request in the meantime. So these shorter requests need to wait for a freed-up space. So internal fragmentation and reserve may sound very similar. Well, they do both reserve certain space in the memory, but with reserve, the space will eventually be used. But internal fragmentation happens when the reserve space is never used until the end of the process. And next. And the last but not least, it's external fragmentation. So with KV caches, we need contiguous memory, but sometimes we just do have the space in the memory, but they're just scattered and not contiguous. So all of this free space cannot be used to process any other things. So let's say, like in this diagram, that we have process 0, 6, and 2 running. But there's all of these gray boxes that represent the free space from previously shorter requests or unreserved space. And let's say that these gray boxes do add up to 20 gigabytes. And now we want to run process 7, which needs all of these 20 gigabytes, but we do have the space, but it's just split it up and scattered, so we still cannot use it to run process 7. Yes. CJ.
I have a question about the external fragmentation. Well, if any other has answers to this, especially Yalu, isn't the well when we're storing the memory when we get the page fault, I mean we will allocate something. So external fragmentation doesn't really happen in nowadays memory. Well, this question is specific for those who have taken OS classes. Yalu, do you know anything?
I remember fragmentation from CSC 120. But so I do remember the buddy system in which the memory fragments are continuously divided by 2 and checked if they are fragmented or not. But I don't remember how the memories that are deemed to be not useful are handled.
Okay. Jacob, do you know anything? I saw you unmuted.
Oh yeah, I was about to say like I think once after a while the memory like the operating system will do like a waste collection to collect these external fragmentation. Like basically put those like allocated memory like together and just squeeze out the external fragmentation for like more like available pages to be like reused. So like if it doesn't have enough space, like the operating system will probably just do that. If there's still not enough space, it will just like use the swap space on the disk. So basically like swap some of the idle process memory, like store it on the disk. And and just you have like more like memory and and
Well, adding on to that, you need to use some library to enable swapping when you're calculating on GPU. Otherwise, it's OOM out of memory. Okay, yeah, sorry to interrupt. Please continue.
All right, thank you. And we'll just go next slide then. But yeah, so with this KV caches, the bottleneck, as mentioned before, that causes these memory waste is the needed for contiguous space for anything to run. And next. But what if we cut this long request into smaller pieces and deal with them separately in the physical setting? So the same way when we like break our crackers or cookies to fit a certain container. But yeah, how do we implement this in real life? So Ian.
So glad you asked. So the developers of this paper, they made a library of code online called VLLM, and you download this, and this is pretty all in one. It has program stuff that you can use to make your scheduler, allocate your memory, run your model, all that sort of stuff. And if we were to look at a big overview of what the VLLM system looks like, it would look something like this. You have your scheduler. It's going to receive requests, like say, for example, it's GPT. You're going to get a bunch of requests from the internet. It's going to manage what devices to send these requests to be processed. And then also, you're going to have a KV cache manager with block tables. We'll explain what those are in a second. As well as these things, which will help decide where you're going to store the KV memory. But first, we mentioned chopping our sequences into smaller chunks, and that is called page detention, and it's based off of a phenomenon that actually, or not a phenomenon, a common practice done in operating systems. And Jacob will explain this.
Right. So what is paging? Also, paging is a concept in operating system where there's a virtual memory space and a physical memory space. So your virtual memory is contiguous, like it has a contiguous address space. Before physical memories, it is divided into pages of the fixed size. So when the program access a data in the memory, that access request will go through the operating system, and the operating system will map the virtual address used by the program to the physical address of the memory. So the OS has to figure out which page that data belongs to, and kind of map the virtual address to the physical address and get the data. And next, please. So why do we need pages to manage and allocate memory? Because this way it allows for algorithms to reduce external and internal fragmentation, reserve memory waste, as mentioned by Flavia. So with pages, it is the basic unit of memory management, and we can do more with it. And so why is it more efficient for memory allocation as well? So you can think of it as, so here's an example, when the operating system needs to allocate a large enough amount of memory to a program. So the memory is very large, so it is very difficult to find a large and contiguous chunk of memory inside inside your RAM. So what the operating system do instead is that it would just look for several smaller pages that are scattered across the memory that are not necessarily connected, so that it can allocate a large enough memory as required by a program. And that's how it works. Next slide, please.
All right. So yeah, page detention divides all your memory into smaller blocks so that you don't have to pre-allocate a bunch of room for your sequence that might grow incredibly large. So that saves you a lot of memory, and this is just kind of a side-by-side comparison of how pages look in an operating system and how memory is managed by VLLM through page detention. Let's talk a little bit more about page detention as it looks while your sentences are being added to. So for starters, over here we have logical KV blocks. And what's kind of meant by that is this is how you imagine your sentence looking in the computer. You know, it's all in order. And then over here we have physical KV blocks, which is how it's actually stored. And when I say block, I mean a chunk of memory. Also, when these diagrams show words, it's not actually the, positionally embedded matrix that you usually have at the start of your model. The words are actually stand-ins for the KV, the rows and columns within the K and V matrices that correspond to those words. So for all the diagrams going on here, I want you to imagine that there's another dimension extending into the screen filled with numbers, and each one of these words is associated with a bunch of elements in the K and V matrices. So, but we're just writing them as words because that's easier to see and understand. Okay, so let's say, for example, you have some request from the internet, and the prompt is Alan Turing is a computer scientist. And, now your model has to generate another word. So logically, it looks like this. But then it's going to generate another word, and then when that happens, your VLLM, all the programs and stuff, is going to take that new word and then it is going to use a block table, which is kind of like a table of contents for your memory. And it's going to take that new word and it's going to add it to the appropriate block in the physical memory. Any questions so far? Yes.
Are you sure that the same piece only keeps one instance? Because why I ask, because besides embedding, we also have inside the embedding, it includes positional the positional values. How do you account for that?
Are you referring to the fact that there's like only one element per word?
No, I mean in a sentence, let's say computer scientist, if it happens at the first two words, the embedding representation will be different once it is at the 10th and 11th word because of the positional embedding.
Yeah, you're right. So could you tie that into what you want me to clarify?
Yeah, then do you keep the same instance of computer scientist on the right-hand side in your physical KV blocks?
I see. Yeah, you would. Because I
they
mean,
have different embeddings.
well, right. So I mean, I get that like in the physical KV block, it looks like the sentence begins with computer scientist, and so that would have you would think that would have, I mean, it looks like maybe it'd have a different positional embedding, but like the point is not that these are actually like sentences, but just like this, but that the memory for the K and V matrices gets split up into smaller chunks. You're just trying to make it easier to allocate memory, but I'm pretty sure that the vectors associated with the words are going to be the same. If I understood your question correctly, I might not have.
The vectors shouldn't be the same because their positional embedding is different.
I see. Could you elaborate more on that?
So in attention paper, we have embedding equals your word embedding plus positional embedding. Even though you have the same instance, computer scientist, this is the same. However, your positional embedding is different. So they add up to be two different vector embedding representations. So my interpretation is that they should have two different computer scientist pieces if you are talking about different queries. For the same queries, you can store it. It is the same instance.
So were you asking if the representation of the words computer and scientist would be different if they were from different queries
Yes.
or from different requests?
They will be different.
Yes, my apologies. Yeah, that's right. Sorry, I thought you were asking if the numbers representing computer and scientist would be different in the logical versus the physical memory.
Oh, yeah. Okay, yeah.
Yeah. All right, cool. So yeah, every new word that gets added on is then going to be physically stored in memory. And then just, here's another example. The next word, mathematician, gets mapped to an appropriate block. Renowned, it's starting a new block now. So now your memory has to choose a new block. And that's kind of what's nice about KV blocks is that you can put this physical memory anywhere. Even if your sentence is in order, logically speaking, you can put those chunks of sentence anywhere in your physical memory, which gives you a lot of flexibility when you're trying to store stuff, especially with a lot of requests coming through, right? This is only one request, but maybe you've got a bunch of things going at once, and then you need to store these chunks all mixed in together in physical memory for different requests. And then that's why page detention is helpful. Does that kind of make sense? If you guys want me to clarify that, just let me know. All right, swag. We move on. Yeah, that's pretty much it for that section.
Yeah, so basically with VLLM and the concept of page attention, we're minimizing the memory waste created by KV cache. So firstly, it's able to eliminate external fragmentation because each request does not require a contiguous memory space in order to run, as explained before, because they're broken apart into like smaller pieces, so they can run in different physical parts. And secondly, it minimizes internal fragmentation because these chunks are much smaller, and most of the time the request will need, let's say, several chunks or blocks. So only the last block would be the one that isn't fully filled. This is a better option than the previous way or the traditional way where they use the maximum length. So the internal fragmentation could be very significant previously. And yeah, we'll see how page attention is able to reduce the memory usage in 3 other LLM serving request patterns, which will be next. Okay.
Sorry, I was muted. So from here we go through several sampling techniques that VLM is especially like good at and geared towards. So the first sampling method is parallel sampling. So typically when we like generate a sequence, like for a query we only like generate like one sequence, but for parallel sampling we're generating several sequence at a time. So how this is like done is that in the final linear like layer of the transformer, instead of just when we're generating the logits, instead of like picking the token with the largest probability, we pick several like the top k number, like top k probabilities, and predicts like several tokens. And so for these separate like sequences, they all share the same like KV blocks for for like for their like query, so the VLM can automatically like keep track of that and not keep like several copies of the same like KV blocks. It can just map them to the same KV blocks. So next slide, please. So beam search is another sampling method, like very similar to parallel sampling. It also like after like each iteration, you also pick like a fixed number of possible like tokens, but it adds an extra like step, which is to eliminate, like just terminate the sequence if the probability like for that token is lower than a certain like threshold. In that case, the VLM will just like free up the KV block associated with this terminated sequence. For example, for block 2, 4, and 8. Next, please. So shared prefix is another sampling technique. So for shared prefix, you would have like some common like prompt, but you have like some like task input. So the shared prefix is where like the KV blocks are the same, and VLM can also like keep track of that and just keep one copy. Next, please. Yes.
All right, this one's mine. So let's say a very unfortunate thing happens and your KV cache it's filled up. It's no more room. So now you have a problem. You've got all these people using your ChatGPT website with their little prompts. Maybe they got a little squiggly line circling their screen because nothing's loading or something. Or at least that's how I like to imagine it. Because, and all right, so actually let's back up. So KV cache can get full because you don't really know how long these sequences are going to run for. So if you are packing your batches full of these sequences and you're iterating over them, they're going to grow and grow and grow and grow. And then eventually your KV cache, there'll be no more room. So at this point, you have to prioritize some of the processes. And how do you do this? How do you decide which ones to prioritize? Well, apparently, there are magical heuristics that you can use to determine which block is least likely to be accessed in the near future. So which sentence needs to have something added to it in the near future. I actually didn't really fully understand what they meant by that, so maybe I should have researched that a bit more before I added it in. But essentially, you take that block that you've decided you don't need to add to at the moment. And by block, I guess I really mean sequence, because when you, so you're going to take that block, the one that you think you don't need in the near future, and you're going to do one of two things to it. You're either going to just delete it. And when I say block, I mean a chunk of KV cache memory. You're just going to straight up delete it and then recalculate it if you need it later. Or you are going to take that block and you're going to move it to some separate section of memory. If you move it to some separate section of memory, that is what is called swapping. And if you recompute it, that's called recomputation. And also, I should specify, it's not just one block. You're not doing this block by block. If you're going to switch or recompute, you're going to take that block and you're going to take every single other block associated with it. Or in other words, the other blocks that make up your sentence. Those are all going to be grouped together in something called a sequence group. And also, it's important to note that for sequence groups are going to include any parallel samples being made. So like if you have like one starter sentence and then it's growing into two separate sentences, those are all part of the sequence group. And so the KV cache memory for those in the instance that that your cache fills up, the memory for all of those together is going to be taken off your cache and moved to some other area of memory, like your CPU or something like that. And that is what the CPU and GPU allocators do. They decide, you know, what groups of KV cache memory will be stored where at which time. So that's what you could do if your cache memory fills up. Oh, yeah. So I actually am not sure if I fully understand this slide. So I'm going to only go over briefly, and definitely feel free to point me out if I got the concepts wrong. But I definitely still want to include it because I love it. So batching, let's say you've got a bunch of requests, and then you decide that you're going to do things the old-fashioned way, and you're going to pad these requests with a bunch of extra memory space just in case they grow long. And so you do that, and then you pack all these requests together in this ugly tensor brick, and then you send them through your system because it's easier to multiply things if it's all one consistently shaped tensor. So it's nice. But it also means that you are not getting as much bang for your buck out of your CPU and GPU because you could be doing more. You could be doing more requests at one given time, and also saving yourself a lot of memory and space. Because, I mean, this sentence is only like a few words long, but then you're giving yourself thousands and thousands of extra units of memory just in case it ends up filling it up. So that's bad, very bad. You don't want to do static batching. What you want to do is dynamic batching. And dynamic batching is going to essentially not pad your requests. It's not going to give you extra room. It's just going to have them go in one at a time, each with their own unique sequence lengths. So that allows you to save yourself a lot of memory trouble. But unfortunately, I said it saves you a lot of memory trouble. I'm actually struggling to remember if it saves you computation time or if it saves you memory. I think it allows you to fit more sequences into your batch at once. I think that's the benefit. But yeah, unfortunately, if you do dynamic batching, you're going to need a lot more KV cache memory. Hence this paper, which talks about how you can reduce the issues with large amounts of KV cache memory. So maybe this slide should have been like closer to the beginning, but hopefully I didn't butcher that. That's some of the basics behind the batching.
And now we get to the evaluation and performance. So for evaluation, the author compares VLM with two of its counterparts. There are other like memory engines for LLMs. So faster transformer is distributed inference engine like optimized for latency. So by the time the paper came out, there was no dynamic batching for faster transformer implemented. So they implemented dynamic batching for faster transformer. And Orca is a state-of-the-art LLM serving system optimized for throughput. It uses buddy allocation algorithm to determine the memory address to store KV cache. And here are some like it tuned like 3 versions of the parameters for Orca. As you can see, and next slide. So how they measure the performance of their system is by normalized latencies. So normalized latency is the mean of every request latency divided by the output length. In another word, that means like the average time it takes to generate each token. So as you can see, all of the graphs, like after a certain request per second, the latency will increase exponentially. And the blue plot is VLM. So you can see that so the request rate for VLM to like for latency to go exponentially is about like twice twice as the best of his counterpart Orca. Next slide.
Can you wrap this through? We know page attention is good compared to other results.
Yeah, we can move on to the next slide. Right, so here's a more straightforward way to understand why like VLM works better is by how much memory is saved using VLM for the two like sampling techniques. So for parallel samplings, it saves from like 6% to 9% for these number of output sequences. And like one interesting observation is that like if you look at the memory saving for beam search, it is much higher than parallel sampling. This is because for beam search, you're not just like having multiple sequences sharing the same KV blocks. You're also like deleting and like freeing up like chunks of memories. So VLM like does that and create a higher like memory saving. Next, please. So here's a evaluation for like shared prefix, and as you can see, VLM also lead Orca by about like twice the request rate. Yes, next please. So we haven't mentioned another like inferencing, like sampling techniques, which is like chatbot. So it is essentially just shared prefix, but we're also concatenating like the previous like conversation to the prefix, pretty much like how you would interact with like ChatGPT 3 or 3.5. So, and it is also limiting the context window to 1024 tokens. So VLM also like outperforms its counterparts.
We can skip this.
Yes, and that'll be all. Thank you all for listening.
Okay, great.